Right, Cole is handing out the schedule for SI. Again, it's entirely optional, it's up to you. The more of this stuff you see, the better. So he's going to start today, I believe, and it's going to be valuable. Now, recitation, because we weren't here on Monday, the Monday class did not get a recitation this week, so I think what I'll do is put the homework back a couple of days, right? I'll certainly get done with 13 probably today and Friday, give you the weekend to think about it. I would like to have recitation on Monday with those people so that they've seen this material again, and then they can try the homework. So the homework will be due, I think, Tuesday, 9 p.m. If you've already done it and you're not happy with your grade, let me know. We can talk about that. But the rest of you, make sure you get that done as soon as you can and keep up with stuff. In terms of where we are at, I'm talking about alcohols and how to make them. And a lot of what we've done so far seems to be similar. It seems to be overlapping. Now, that's a good thing because I'll say, you know, somebody who's experienced in the subject, it's a good thing because you're not learning that many mechanisms. You're learning a couple of simple mechanisms. But for you looking at all of these things, thinking about, all right, esters give primary alcohols, esters give tertiary alcohols, that can be confusing. And again, just keep on top of it and make sure that you're comfortable with what we're talking about. We left off with this slide, I think. We were talking about the different outcomes when you add nucleophiles to carbonyls. If you start with an aldehyde and you add a carbon, you get a secondary alcohol. If you start with an aldehyde, you add hydride, like borohydride or lithium aluminium hydride, you get a primary alcohol. Don't get lost on that detail. That should be obvious. If you understand the mechanism and what's being used here, hydride is negative hydrogen, Grignard reagents are negative carbon, then that should fall into place. Mechanistically, we've only done two so far. We've done nucleophilic addition and nucleophilic acyl substitution. And what tends to confuse people is down here at the bottom. You will see that the reaction of an ester with a hydride or with a carbon nucleophile is two mechanisms put together. So in this reaction, we have lithium aluminium hydride. We might write excess there to make sure we know that we have enough. We get one reaction, which is substitution, in which the OR group is lost and replaced by a hydrogen. That produces an aldehyde. That's even more reactive than the ester starting material, so it goes again. And that's a sequence of nucleophilic acyl substitution and then nucleophilic addition. And we'll do a lot of that this term, just sort of moving around different parts of mechanisms to come up with apparently or seemingly a new process. I left off talking about this process. This really confuses people. People tend to get stuck at this point. They tend to get to the ketone, which is the first product of substitution, and then they forget, okay, that ketone is now more reactive than what we started with, so I should go further and make sure we do, and that is a very useful, very powerful method for producing tertiary alcohols. So keep up. Be cataloging things, be making flashcards. I've seen some people with small notebooks. That's a good idea. So you've got something in your pocket. You can always be practicing this stuff, and it will help as we get towards an exam. What I'd like to start talking about today is some of the problems that organic chemists face that biochemists don't. Biology seems to have worked out all these problems, but organic chemists are still trying to work out how to protect things, how to do chemistry in an unfriendly environment. And by that I mean, in this type of situation, we have produced in the lab some type of Grignard reagent by adding Mg to alkyl halide, and we've got our species here. Again, I prefer to write it like this. If you look on the Michigan State website that I tend to use as a second reference, he also writes it like this. I'm a fan of this structure. The problem with these reagents is that they're very sensitive. You can buy them, you will get them shipped to us by UPS or whoever. We can buy solutions of them, but often it's better to make them yourself because they do react quite quickly. If you get humidity in there, if you put moisture next to these things, they will react. So we have to be sort of cognizant here of the fact that these are negative groups, just like hydride, are very nucleophilic, but they're also very basic. And if they're very basic, that means if you put them in the presence of an acidic proton, you will get acid-base chemistry first. Acid-base reactions are typically the fastest things that we will do. So for example here, if you put that R- in the presence of a carboxylic acid, it isn't going to attack here first, right? That's what's been happening with the aldehydes and ketones. The R- group has gone for the carbonyl. But with the carboxylic acid here, or as we'll see in a second, more complicated systems with other functional groups in there that are acidic, you will get reaction at the proton. And maybe you don't want that. That's a problem in synthesis. If your carboxylic acid is quenching your nucleophile, that's a problem. So be aware here. These things, these Grignard reagents are very basic, and when you make this in the lab, be aware of that so that your glassware is dry. And if you put it in the presence of some molecule that has an appreciable pKa, like an alcohol or water or carboxylic acid, you will get an acid-base reaction. And so far, what's the pKa of that conjugate acid if this happens? If say we start with methyl magnesium bromide, what's the pKa of that product? 50 or 60, right? It's really high. So that's it. It's dead. It's not going anywhere else. That's the end of that reaction. So maybe what you've done is you've destroyed your Grignard reagent by not being very careful, and not recognizing the fact that they are bases too. We want them to react as nucleophiles typically, but if there are protons around, you will get an acid-base reaction. Now, that's a fairly simple example at the top. What isn't so obvious is when we start doing multi-step complex synthesis and we approach molecules like this. We have a system here in which we have a secondary alcohol in the same molecule as the bromide. Maybe that alcohol won't react with that bromide, but as soon as you start to think about doing organometallic chemistry with a Grignard, you have a problem. Because if you were to put a negative or delta negative charge on that carbon, and you have an alcohol within striking distance, it won't ignore it. What will happen? You'll get an acid-base reaction. One will go after the other. You can't avoid that. So to teach this is kind of, it's kind of fun and kind of interesting to try and get this into people's heads. But what we need to do is to get rid of the alcohol temporarily, right? We need to block it. And it's similar, I don't know if anybody's done any painting in their house and you don't want to paint the ceiling and you just want to paint the wall, and you might cover it with something. You might put some masking tape or some painter's tape on the thing and get the piece that you don't want to paint out of the way temporarily, paint what you want to paint, and then get the tape off, right? You're blocking the stuff that you don't want to make a mess of. So I'm going to do that here. I'm going to use something called protecting group chemistry, which is a huge subject in its own right, to temporarily get rid of that alcohol so it doesn't react with our Grignard, and our Grignard then can be used to react with whatever else we want to. But then at the end of the day, I want my alcohol back. So the key here is temporary. We have to think about some way of doing this in a temporary sense. So this slide, a lot of people have trouble with this. If you're struggling with this, you'd like everybody else. Don't worry about it. Ask questions about it. We'll try and come up with analogies to make it make sense. So here's the key. We want to produce a Grignard reagent at this end of the molecule. But the starter material we have access to has an acidic functional group inside that molecule. If you were to put simply MgBr here, that carbon, which is now negative, will go after the proton on the alcohol. You cannot do that. It just kills the reagent. It's not going to do anything useful. So what we need to do is to get rid of the OH group temporarily. And that's where the black box comes in. Think of it like that. You're just putting it into some safe environment whereby the Grignard reagent can't go after it. You're making it incompatible with the Grignard reagent so it doesn't react. And we'll use this term from now on, a protecting group. Protecting group chemistry is a pain because it means extra steps and extra work, and you have to put them on, you have to take them off, you have to make sure that they're compatible with the conditions you're trying to use. And we'll talk maybe about 2 of them during this semester. But I have a book on my shelf in my office which has about 1,000 of these things in there for all different situations. It's a big deal because we have to protect things along the way. So here we go. Make sure we're trying to follow this. What we're trying to do here is some carbon-carbon bond type chemistry where we're making this bond in this product. We're trying to do what we did the other day, which is add carbonyls, add an aldehyde, add a ketone, something like that. So the Grignard goes after that carbonyl, and it does not deprotonate the alcohol. So this alcohol has to go someplace. In this example, what we'll do is derivatize it as an ether. We'll make it less reactive, so the Grignard ignores it, and the Grignard then goes after the piece that we want. In this case, we want to do an intermolecular reaction with a ketone to make that bond. So we get rid of this. And we'll use one particularly useful procedure for this, using a silicon derivative, and then hopefully later, maybe we'll do one more later, but mostly we're just giving you the concept. And I think as we go through to the end of the term, keep in mind, this is why chemistry is expensive, and this is why chemistry is difficult, because we have to think about these things. And biology has perfected all these things by, evolving enzymes and whatever that just do one job at one part of the molecule, and it doesn't really matter what else is elsewhere. So organic chemistry is trying to catch up. So this slide, this can be confusing. You will see it. It is something I want you to be happy with. What we'll do is turn this alcohol into something called a trimethylsilyl ether. And that's simple enough. You've got 3 methyl groups, so there's where trimethyl comes from. Silicon, silyl, and an ether is a carbon-oxygen, in this case silicon bond. We've seen ethers so far being carbon, oxygen, carbon. But you think about where silicon is in the periodic table. It's the row below carbon. It's got very similar properties to carbon. So this is a silyl ether. Now the idea is that silyl ether, which will be abbreviated TMS, does not react with the Grignard, for the simple reason it does not have an acidic proton. No acidic proton, no acid-base reaction. So it's a way of temporarily getting rid of that alcohol and making that system incompatible with the Grignard, so the Grignard can do what you want it to. So how do you make these things? Well, it's fairly simple. You need an alcohol. It can be any type of alcohol, really, primary, secondary, or tertiary. And you introduce what we call TMS chloride. And TMS chloride is nothing more difficult than, say, T-butyl chloride. right? If you think about carbon and silicon being related to each other, it's somewhat similar to T-butyl chloride. And what will happen here is this. We'll get nucleophilic attack on the silicon, and we'll lose that chlorine as a leaving group. Now, people will say, isn't that disallowed because it's bulky? Well, the next slide will disprove that. The next slide will show you why this works. What do you think ET3N is going to be used as? A base, absolutely, great. Now, think about what the byproduct is here. What is the byproduct of that process? What's left over? HCl, acid, right? So let's get rid of that so it's not taking any part in the reaction, it's not messing things up. So the ET3N is simply going to neutralize the HCl to get it out of the game. Okay, that's all it does. Now, if we think about pKa's, the ET3N is probably not basic enough to deprotonate this to any great extent. If you take that off, you make O-, which is a very powerful base, and you would make ET3NH+. I'm not sure we've mentioned this yet, but the pK of that guy, just to keep everything thorough, is about 10. Okay? So you'll see that the left-hand side is favored. But the ET3N can mop up the HCl once it's produced. What have we used in the past that's done the same type of job? It's a cycle with a nitrogen in it. Pyridine, right? It's very similar to pyridine. In this example, it's easy to use. This one is easy to use. It's low boiling, and it does the job. And what you get is this species, the trimethylsilyl ether, which can be abbreviated OTMS. And what we've done now is put some masking tape, some painter's tape over the piece that we don't want to make a mess of, and we can go do our business, do our chemistry somewhere else, and then come back and take that off later. And hopefully what we've got back is the alcohol. So there's the outcome. You're going to see this in synthesis problems. You'll have to use it in problems that have this issue. You'll decide, okay, I need to block something somewhere, and typically it will be a TMS ether. So that's how you make them. And the story is that they don't react with Grignards. So some people might be sitting there going, well, you just said that this is analogous to T-butyl chloride. And if you go back to that slide, what mechanism am I kind of showing here? What is this mechanism over here? What does it look like? Nucleophile going after something and kicking a leaving group out. What's that? That looks like an SN2, doesn't it? But T-butyl chloride doesn't do an SN2. Why not? It's too crowded. It's too crowded, it does SN1s. So all of a sudden we're saying that this big, seemingly bulky thing can do an SN2. Well, the answer is fairly clear, and it's analogous, and it does make sense in terms of the periodic table. You look at the periodic table over there on the right-hand side, carbon is at the top, silicon is below it. What does that tell you about the size of silicon? Smaller or bigger? Bigger, okay? So that means that if silicon is bigger, then the methyl groups are further apart from each other, and that silicon is accessible. You can get to that silicon by using an alcohol as a nucleophile. And I'll tell you this, there is a very strong bond between O and S, right? There's a very thermodynamically favored bond between oxygen and silicon. And if you think about where that shows up in the world, what's the most obvious example of where silicon and oxygen show up in something? Quartz, for the geologists, or even more simple, anybody who likes the beach? Sand, right? It's a very strong bond. Silicon-oxygen bonds are very strong. So what we've got now is a thermodynamically favored system in which the nucleophilic attack gives you a pretty stable molecule. The OTMS ether is pretty stable, which means you're going to have to hit it with something very powerful to get it back off. So what we've done here is protection. We've put on the silicon group. We then do our chemistry elsewhere. We try to get the product that we want, but at the end of the day, we don't want that silicon ether in there. There are no natural products or medicines that I know that have a silicon group in there, at least a TMS ether. So we have to get rid of it. It has to come off. So this is how you put it on, and this is how you take it off. Now, the only thing that realistically we can use in the lab that will do this and swap a very strong silicon-oxygen bond for something better is fluoride, right? The one that we use the most of is fluoride, F-. Now, where's the most obvious example of F-? Anybody know this? Geology types? Fluoride, right? And where does fluoride show up? Where do we get NaF? Toothpaste. If I'm not wrong, it's in the toothpaste, right? You grind it down and you use to clean your teeth. Fluoride loves silicon, okay? Fluoride loves silicon. So if I expand this out, SiMe3, and I have my O attached, fluoride's like a little piranha. It goes after that thing and it says, boom, goodbye. It kicks out the silicon. And if you're in the presence of a little bit of water, which you often are with these materials, you can get a protonation to give the alcohol back. Now, the one that we'll use the most of is something called TBAF, which I will explain in a second. And this F- now is going to be the method that we will use to unblock our alcohol to get back to where we want it to be. TBAF, I'll explain the structure in a second, comes as a supposedly anhydrous mixture, but it's notorious for not being completely anhydrous, and that water that's in there will serve as an acid to give you the OH back. So thermodynamically, this is good, but SiF is better. And sometimes you have to be careful, because if we use certain types of glassware, which contains silicon-oxygen bonds, the fluoride goes after the glass, starts eating away the glass, starts etching the glass, and you have to be careful what type of glass you use. It's that reactive. So far, OH the problem, get it out of the way by blocking it as a silicon derivative temporarily, and then when we're finished, we'll take it back off and go back to the alcohol. And that's where this slide shows everything put together. The Br group here, we're going to try and make it into a Grignard. We are going to take, we have a problem with that because it would react with the alcohol, so let's get the alcohol out of the way. You'll see it abbreviated like this, or you'll see it written as this, Me3SiCl. Okay, that's the same stuff. And in the presence of Et3N, we will do a protection, which is nothing more difficult than a substitution in which the O replaces the Cl, and we get a strong oxygen-silicon bond. So now we have an O-TMS ether. That problem is now gone temporarily. The O-TMS group is now blocked. We can then do the chemistry. We can put the Mg in. The Mg goes here to make a Grignard. We then put an electrophile in. This place is a ketone. That ketone is electrophilic, and so it'll react with the nucleophile. We'll do nucleophilic addition. Why not nucleophilic acyl substitution? No leaving group. No leaving group here. Okay? No leaving group. And at the end of the day, what we'll do is we will then quench, because we had an alkoxide, and that gives us a tertiary alcohol. And you've got to think about this as synthesis, right? This is, think about chapter 12 and where we came from last term. We'd made that bond. That will be your target, but there'll be a problem with it because you have to block something. At the end of the day, we don't want this. We want to get rid of this, so we'll put TBAF in there. And you'll see it written as TBAF, and you'll see it written like this. And on the exams, old exams, problem sets and what have you, we write it in different ways so you get familiar with it. You know what it looks like. And so that is a source of F-. The T-butyl groups here are nothing more fancy than trying to solubilize this stuff into the organic solvents. Those alkyl groups will help solubilize this stuff, and away we go. We get F- going after the silicon, booting out the oxygen, pick up a proton from the water solvent, and we are finished. Michael? At the last step, well, TBAF usually comes in a solution of THF, okay? And looks like that, which is a good organic solvent. But the problem is it's very difficult to get this stuff completely dry. So there's always a little bit of water in there, and that water can serve as the acid. Like with the reduction with borohydride in solvent that were protic, you had a solvent present to actually protonate at the end, very similar process here. Okay? So it's all in there. Everybody happy? I've gone very, very slow so far on purpose to make sure that we get out of holiday mode and we get into serious mode. On Friday, I will just go completely mad. I'll start laughing hilariously and just go crazy. So make sure we're keeping up, right? Because when we get to 15 and we start doing spectroscopy, wow. Anybody have any questions here? Anybody at the back? Dominic. Okay, so there's the TMS ether. The H has gone with the base. This base here is picking up that H. That's what the triethylamine is all about, is to pick up the HCl. So what we've done here is something that is, we'd spend 5-10 minutes on it in class, but this is something that is huge, and in graduate school, if you do a PhD in this stuff, you spend a semester on protecting groups, because it's that important. You think about people using tools in the trade, painting or something, or decorating. It's one of those tools of the trade. It's the masking tape. You can't avoid this stuff because it's necessary to get the job done. So we put the TMS ether on, we do the chemistry we want to, and then we take the TMS ether off. But on top of that, you've got to know about Grignard reagents. You've got to know about which carbonyls do what. The aldehydes and ketones do addition. The esters do substitution followed by addition. That stuff that should be in there now. That's what you're going to get tested on pretty quickly. Okay, restation will do more of that. Now, I'm not going to spend a lot of time on this because it is tangential. The author of the book likes to put these derivatives in, and then we spend 2 chapters on this stuff. There's a 2-chapter sequence of this stuff coming up anyway, so I'm not going to spend a huge amount of time on this, except for the fact that The chapter is all about alcohols and phenols, so we ought to spend a few minutes on phenols. We already talked about some of these things last term in the sense that they're useful in food preservatives. They are antioxidants, and so they can help with food preservation. And we can make them by chemistry that's coming up around about spring break. Benzene can be turned into this material here. You don't know that mechanism yet. You will in the near future, so I can't hold you to it. What do you think this is? Look at the type of chemistry that's happening here. Just give me some opinions. You're replacing an H on a CH bond with O2. What do you think? What type of chemistry? Oxidation, absolutely. Auto-oxidation. And what did that involve? It was radicals, right? Radicals, because O2 is a diradical, and we'll get initiation, propagation, all those steps in which you replace the CH with the O. Have a look at it, think about it. There are some mechanisms here for those of you who are getting this stuff that can be kind of fun just to play with. And eventually, after a hydrolysis process, you make phenol. There are other ways of making phenol. We'll do the Dow process later, but this is one way of doing it. And I'm not going to hold you to that mechanistic sequence, but we are going to be concerned about the fact that phenols are useful in terms of oxidation reduction chemistry. In terms of other things that we have done, well, we need to think about alcohols as precursors to different syntheses. If you can make an alcohol, you can go anywhere. If you can make an alkene, you can go anywhere, because you can go backwards and forwards between alcohols and ketones and alcohols and alkenes, and they're very much central to what we've been doing. In this example, looking at the starter material, is it primary, secondary, or tertiary? Tertiary, right? And we're treating it with HX, and HX is HBr, HCl, HI, like it was last term. In the first step, we protonate. We did that in both the SN1 and the SN2. Then you made a decision, and the molecule decides which way to go. In this case, why does it dissociate? Why does the leaving group break off? Why doesn't the nucleophile just go after the carbon? It's too crowded. It's an SN1 process. It's too crowded. If you added more nucleophile here, does it go faster or stay the same? It stays the same, because that nucleophile is not involved in the rate determining step for that process. And what you can do very quickly is go to these materials which we find very useful. Halides. There aren't that many halides available from nature, so we can make them very simply by SN1 chemistry. I would make a note, if you're struggling with that, go look at my website, the mechanism page, go have a few minutes and decide that you're okay with it. It's the same principles from last term, which you were tested on not more than about a month ago. So we should be okay with that. We can also do SN2 chemistry. The decision again is based on the fact that this is primary, and therefore it cannot handle a carbocation, so what it will do instead is do an SN2 reaction. It's accessible. Once you protonate, what is the whole point of doing the protonation? What does that help the system? It's a much better leaving group than it was as hydroxyl. So you protonate this thing, and then the SN2 is all about the nucleophile coming in from the back. If it was stereochemically important, what would happen? What type of stereochemical issue here? Inversion, right? And that gives you, in this case, a primary bromide. Now, we do need to think about other ways of doing this, because as the molecules get more complicated, and by that I mean getting towards engineering problems, getting towards biomedical type problems, HBr is not very good. HBr will react elsewhere. We're building up polyfunctional molecules in which over here, let's say over here, you've spent the entire past couple of years making something that's very, very expensive. And you threw HBr into this system, it'll just destroy that. You'll go backwards, and it's just a waste of time. So we need to develop methods that are alternative to just using the acids. A very useful method is this. Zinc chloride, in the presence of an alcohol, gives you an acid chloride. Chemically, not too much to it. Give me a phrase that describes what zinc chloride is behaving as there. Not necessarily a catalyst. What's it behaving as? What's it doing? It's accepting electrons. Let's think chemically. Electrophile is one way of saying it. What's another way of saying it? That's more sort of general. Lewis acid, absolutely. This is behaving as a Lewis acid, and we need to be aware of that as we head towards benzene chemistry. Some of these metals are very, very good at helping us do chemistry. So what we've done here is set up a leaving group, and that leaving group is analogous to the water breaking off, and the halide behaves as a nucleophile. And how would you test this? How would you test that this is an SN2? Add more nucleophile, what should happen? It should get faster. Those are the concepts that we hammered last semester, and we should be okay with. Pierce. The second chloride, well, you could imagine at this stage that one of these things breaks off to give the zinc a neutral charge. It's ionic, isn't it? So it's going to be floating around. Jessica. Oh, you can. If it's a simple system, yes, you can. You did that in lab. But the problem is now is over here. We're progressing into the more complex stuff. Certainly by spring break, the molecules get quite large and quite intricate. And if you spent all that time making that in the lab and then you throw HBr in there and it chews everything up, it's completely counterproductive. So we're developing more subtle approaches. Michael. You can do that, but my guess is that's HCl gas, which doesn't contain any water, so it's not necessarily hydrochloric acid. Yeah. So these are just little bits and pieces that help you do the job, that help us, enhance the toolkit. And you've seen some of these things. If you want to do an SN2 reaction on an alcohol and you want to avoid those acids, we already dealt with the tosylates. And tosyl chloride, you should remember here, this thing is obviously, it's abbreviated, but that abbreviation can be dangerous. It's like biology with all these acronyms. What does it really mean? We need to worry about a structure. So we might think about a tosylate as being a system that is a benzene ring. It had a methyl group at the end, and this does nothing for the molecule whatsoever. The business end of this molecule was the SO2Cl. That was tosyl chloride, TSCl. And you could imagine now that the OH group, which is a poor leaving group, can go after the sulfur here and kick out the chlorine. So what's the chlorine behaving as? A leaving group, as ever. And that will produce what we call OTS. So that's basically this oxygen attached here instead. OTS is that. And now why is it a good leaving group? We said the OH at the beginning was poor because if you break it off, it becomes hydroxide, and that's a very, very poor leaving group. Why all of a sudden is TS okay? Resonance stabilized. It was resonance stabilized. If you put charge on this oxygen, you can delocalize it into the sulfurs quite easily and into the oxygens, and so therefore it's very good. So we've got the sequence now of taking a poor leaving group and enhancing it by using tosyl chloride and pyridine. Pyridine again is there to mop up HCl, the byproduct, take it out of the game, sequester it, and then we can think about this. Some nucleophile comes in and kicks out the leaving group. Now what's that dash about? That's an inversion. You're at a secondary starting material, that is chiral. It's an SN2 process. You can measure this because you'll see the inversion. And so tosyl was a great way of enhancing the leaving group ability of OH, which we've already covered, and is still game for synthesis this term. There's the sequence. Activate the OH with a tosylate, and then stick in some halide, some nucleophile, and away we go. Mr. Homan. Using what as a protecting group? The OTS as a protecting group can be used as a protecting group as long as what you have else to do is mild type of chemistry, because OTS is a very good leaving group in E2 and also in SN2. So if your reagent that you're trying to use after you've blocked with TS is nucleophilic or it's basic, you'll get E2 chemistry and SN2 chemistry, which is probably not what you want. So in a sense, let's say this. It's a good question. I would say the OTS group is used to enhance the reactivity, and the TMS group that we just dealt with is used to suppress the reactivity. They're quite opposite. That's okay? Lots of questions coming up this week. I expect to be busy. Now, another way of putting a halide on there, which does not require the use of a powerful acid, is the use of SO2Cl. I'm sorry, SOCl2. Thionyl chloride. I don't think that phrase is on here, so let's use that so we know what it is. Thionyl. Thio is usually a sulfur. Thionyl. Okay, suggests that it's an acyl group, and obviously the chloride for the two Cl2s attached. Thionyl chloride is this stuff. Mechanistically, it's on my website. Not much to this. It's very similar to things we've already done. I would like you to know this. In the first instance, what's happening is that this is behaving as a nucleophile. And it's going after sulfur. Why does it go after sulfur? Why would a nucleophile be at all interested in that sulfur? What is that sulfur attached to? If the alcohol is behaving as a nucleophile, what is the sulfur behaving as? An electrophile, right? It's an electrophile, something that likes electrons. Why is that sulfur in need of electrons? It's attached to electron withdrawing groups. It's attached to chlorines and oxygen. It's electron poor. So it makes sense that the oxygen goes after this. Now, I want to try and teach this so it's sort of unified. We already did some of this stuff, okay? And we'll do lots of it later. That's an acyl chloride. That is an acyl group right there. R-C double bond O. You get better at chemistry and you start to understand things and have to memorize less once you start to see families and start to see patterns. So to a chemist, that C double bond O in that molecule is completely analogous to this SO double bond. They're very similar. It's a sulfur carbonyl, if you like. So we have a situation now in which our electrophile has a leaving group attached. If you attack an electrophile that has a leaving group attached, what type of process do you get? Do you get addition or do you get substitution? You get acyl substitution. So let me get rid of some of this noise. That is very much like an acyl system. And in that first step, you put that next to the ester reactions that we just did with hydride, with Grignards. It's very similar. 2 electrons into the sulfur, 2 electrons up onto the oxygen. But because we have these leaving groups attached, it does not stop there. Now, we gave this type of intermediate a name in that type of chemistry. What was it? Tetrahedral intermediate, right? You've got to keep up with this stuff because it's going to get very, very busy very soon. And this is the second term, right? So the discipline is important here. That's the second step in an acyl substitution. It's completely analogous. Mechanistically, what that leaves you with is this species. And now we have a proton that we have to get rid of. This proton needs to get mopped up. What do you think about the acidity of that proton? Look at what it's bonded to. That oxygen is bonded to a proton and 2 other things. What does it remind you of? Hydronium. Hydronium species, right? Hydronium is acidic or not? What was its pKa? Negative 1.7. That's pretty acidic. So do you expect this species to be acidic or not? Of course. You put a proton on a positive oxygen, that's acidic. So now all we need is a weak base to go after it and mop it up. And that gets us to this. And this is the key species for the rest of the chemistry. What's going to happen now is that this will behave as a leaving group. And as it says there, obviously it's a good leaving group. But why is it good? All right, primary system, that suggests SN2 all day. Why is this good at breaking off? Why should that be such a good leaving group? Think about the tosylate. Why was the tosylate a good leaving group? Resonance stabilized, right? Resonance stabilized. So you had an electron withdrawing group taking electrons away. That's always a good situation. This is analogous, except you get a little bit of extra here. In this case, you can make SO2. SO2 is simply the loss of that molecule, which is explained by that arrow and that leaving group. Now, this is very powerful because anybody know what SO2 is in physical terms? What do you think? Is it a solid, liquid, or a gas? It's a gas. And so it evolves. You get rid of it. Now, we're going to start a very complicated, very deep conversation about, I hope it's a conversation, I hope I'm not standing here, about equilibrium. Because you'll need that for biochem. You'll need it for pchem, things like that. SO2 is evolved from the reaction. It gets lost. So is this process reversible or not? No, it isn't, because you got rid of it. So it's a very nice way of making chlorides. This is a nice liquid to very easily work with. You get the chloride out as the product in high yield, and SO2 is lost. So it's a very useful reaction. But it's completely analogous to the OTS system. And I want you to start thinking like a chemist and start putting things together in groups and families and patterns so that everything isn't just a bunch of noise. It becomes a family. And it becomes something that you've got an opinion about because you're okay with the earlier stuff. As long as you're okay with the earlier stuff. Everybody looks worried. What's that about? Everybody's sort of sitting and chewing their fingernails. Oh dear. We can go back and do 3719 again if you want. No, because it won't get you anywhere. Okay. Very powerful way of doing this. An analogous way of doing this is to use PBr3. This stuff is not much fun. And this stuff is quite reactive. How about a method that takes an alcohol and turns it into a bromide? Because we know bromide so far seems to be our favorite leaving group. So now we can use something called phosphorus tribromide, PBr3. I'll write it out like this, which you will see in equations, PBr3. And again, maybe you know this, maybe you don't. Some elements have a real affinity for oxygen. Silicon has a real affinity for oxygen. Okay, sand. You can't do an awful lot with sand, right? Yeah, it's difficult to break down. It's a very strong bond. Another one is oxygen and phosphorus. And the geologists will find this interesting. You know, phosphorus is an element that you find everywhere. But in nature, phosphorus is difficult to find. I don't think it even exists in nature as the 3-valent species, right? It always wants to exist as the 5-valent species. Now, this is one of these elements that's further down the periodic table, and it can expand its octet. What does that remind you of? What does that phosphorus acid remind you of? sulfuric acid, right? It's analogous to sulfur. Look where they are on the periodic table. They're next to each other. They can expand their octet. So we can get sulfur 2, sulfur 4, sulfur 6. We can get phosphorus 3 and phosphorus 5. Biologists, where do you see this all the time? Where do you see these types of groups all the time? What holds your DNA pieces together? Phosphate linkages, right? Phosphate linkages in the +5 oxidation state. It's kind of a useful temporary linker. So this type of process here is dependent upon +3 phosphorus wanting to become ultimately +5 phosphorus, right? Wanting to expand its octet. But what we'll do here is just follow the sequence through to this stage, not worry about where that goes. Eventually it goes to the +5. But what we'll do here is activate an alcohol by adding phosphorus. Instead of using sulfur, we'll use phosphorus. It can be useful in certain instances. So what's going on here? Give me a phrase that might describe that mechanism where this alcohol goes in and attacks that phosphorus and kicks out a bromide. What does it look like? Looks like an SN2. Certainly does. It looks like an SN2. And then in the second step, we've just liberated Br-. Br- broke away, and it became an independent anion, and that's nucleophilic. And what we've got now is a strong, I'll see if I can do this without making a mess, that OP bond is very strong. Okay? That's the whole driving force for this, is making oxygen-phosphorus bonds. You'll see that a lot later. So what's happening here is that this species looks an awful lot like H3O+ or H2O+. Looks like a protonated OH group, not much different. It looks like the species on the last slide with SOCl2. It's activated as a leaving group and it can break off. So in this step, Br- acts as a nucleophile. How do you know it's a SN2? You're attacking a primary system, nothing mysterious about that, and you get a bromide. Mechanistically, nothing different. We've done SN2, we've done acyl substitution today, but with different atoms. And again, if you're behind on this stuff, it starts to get overwhelming. Just keep up. Okay, so here we have some ideas now of how to do synthesis. At the end of this chapter, which will probably be Monday at this point, we'll be looking at how to put all this together. And let me go forward a few slides. At the end of this chapter, we get back to some of these schemes. Some of these schemes that, all of this stuff is thrown at you all at once. And the whole point is that you know this stuff by now. You won't remember it because we've had a 5-week break since then, but that's where we are. You need to remember those things. So my job today and Friday is to get through to that so we can use this stuff in a useful way to start doing organic synthesis. At the bottom there, you want to turn your alcohol into something useful, a halide. You have alternatives now. Make sure you're happy with them. Right, what else can we do with alcohols? We'll mop these things up today and then we'll talk about oxidation. How do you know this is an E1, not an E2? It's crowded. The substrate is crowded, so that favors a carbocation because it will be a tertiary carbocation. And carbocations are stabilized by what? Hyperconjugation, which is sharing of electron density from adjacent single bonds, of which you have many in a T-butyl system. Okay, secondary less so, primary won't happen because you don't have much. So in this sense, it also depends upon the conditions. In this sense, is the pH less than 7 or greater than 7? It's less than 7. If you're not happy with that and it's not there instantly, get so, because we're about to do a lot of stuff that depends upon what are the conditions. Is it acidic, is it basic, very quickly. So what's the first step in that reaction? Protonate the OH. Protonate the OH to make it a better leaving group. In this example, why not get an SN1? Well, the answer was because the conjugate base of this stuff is very, very stable. It's not a good nucleophile. Bromide is a good nucleophile. So HBr gives you SN1, H2SO4 gives you E1. And the heat, there was a long story about the heat from last term. What was that about? You're going from single bonds to pi bonds. Is that usually a good thing or a bad thing? Bad thing as far as the carbon is concerned. So what did the heat do? It promoted the elimination based on Gibbs equation, right? Delta H is delta G is delta H minus T delta S. And what are we trying to increase? Which component are we trying to increase and trying to boost by raising the temperature? The entropic factor. Yeah, it's all in there somewhere. Just has to come out at some point. Entropic factor. So we typically heat those things up. And the take home from what we just did there is that alcohols, which we are making now, are a very, very, very useful source of alkenes. And alkenes themselves are a very, very useful source of other things. So this is a review. There's nothing fancy here, nothing too complicated. In this example, we have to worry about an issue where we have a choice of where to put the pi bond. And this is what? What type of selectivity is involved here? Regioselectivity, right? Regioselectivity is all about where, region, and in this case we have a choice of where to put the double bond. On the left, the major product, on the right, the minor product. What was the background to this? Why is on the left major? We've got carbons attached to sp2 carbons. The more carbons, the better. What rule was that? Zaitsev, right? Zaitsev. It's all about Zaitsev chemistry, where the more substituted alkene is favored over the lesser substituted alkene. Again, 3719 chemistry. Well, SN1s were a bit problematic. E1s were a bit problematic because they give you a carbocation. What can carbocations do that can be a bit of a nuisance? Rearrange, right? That was a lot of fun last term doing those things. So if we can avoid them, let's do so. And to avoid them, let's do E2 chemistry instead. This is very, very useful synthetically because you can pick and choose where your double bond goes. Hofmann versus Zaitsev, the size of the base makes a difference. The alignment of the proton makes a difference in terms of fast eliminations versus slow. And so in the first step here, tosyl chloride, alcohol, make a good leaving group, and then put methoxide on, or ethoxide in. And that's behaving as a base. And let's say you didn't want to take off the Zaitsev proton. You wanted to take off a proton from a less crowded place. What would you use instead? T-butoxide, right? So those are useful devices that we had from last term to be able to do this synthesis. Big deal synthesis this year. Have to be able to do it. Well, it's Friday. It's time to wake you up. No, it's not Friday. It's Wednesday. It just feels like a Friday. We'll lead into Friday, and then Friday I'll scare you, right? This is key to metabolism. It's key to organic synthesis in terms of setting up the ability to knit molecules together, whether it be us doing it as an organism or somebody in a lab doing it as a chemist. And what we've done to this point is we have taken aldehydes and ketones and we've gone in this direction to introduce that H. Now I'm going to take my time with this. This is important and it's very, very powerful. Tell me about that carbon there. Delta plus or delta minus? Delta plus, because the oxygen is overwhelmingly more electronegative and it wants those electrons. Plus the carbonyl is even more polar because it's pi electrons we're talking about, right? And pi electrons are weakly held, so the oxygen is greedy and tries to grab them. So that is a very positive carbon. So the partner over there is the alcohol, which differs from the ketone by the introduction of two hydrogens. That's a reduction every day. You might also think about it as, well, this carbon over here on the right was bonded twice to oxygen. On the left, it's only bonded once. If this sounds like recitation, it does. Yes? And it's important, and we need to get that idea into us very quickly. The oxidation reduction chemistry here should be able to be worked out by looking at the change. Now you have to decide what reagents to use. What reagents will bring in the required pieces here? Say again? Nope. LAH. Now, it's a good point. It's a good point. Exactly. We're doing this. That's a good point. Listen to this. This will help. I need to bring a hydrogen into that carbon. Okay? In that sense. Why doesn't it make sense to bring in H+? Why does it not make sense electronically and chemically to bring in H+ to that carbon? Because it's positive. They will repel. Yeah? So I bring in instead H-. And these are clues that start to help you work out what to do. What is an equivalent of H-? What have we developed here to be able to use H-? Sodium borohydride. Anything else? LAH. There's a clue. That's what you need to do. As you're designing syntheses, you'll be scribbling things down, you'll be making a recipe, and then putting it all together. So I do need H+ eventually. With borohydride, the H+ came from the solvent. With lithium aluminium hydride, the H+ comes from the acid that you added in the second step. But you've added H- to one carbon, and you've added H+ to the oxygen in a very simple, logical, electronic sense. We did that. Now, this is even more fun. Okay? Oxidation, metabolism, respiration, things like that. Breaking down carbon-based molecules to release energy. A lot of oxidation chemistry. We need to be comfortable with it. What is happening in this sense is we are removing hydrogen. We are getting rid of it, and electrons somehow end up in that pi bond. So we've got to be careful here. If I'm oxidizing something, I need an oxidant. I don't need a reductant. But every time you have an oxidation, what has to come along with it? A reduction. You have to have the opposite. They have to couple together. So I'm going to require, in this type of process, not reductants anymore, but compounds that we'll call oxidants. And your job over the next few days is to work out what these things are. It's how to get rid of the hydrogen this time to go back to the carbonyl. And again, that's powerful because alcohols are everywhere. They're very cheap and easy to get hold of. We can turn them into carbonyls by doing oxidation chemistry. At the bottom is something that you will struggle with, most of you. There is a relationship here between the types of compounds we are using. Ketones are related to secondary alcohols. Primary alcohols are related to aldehydes. Aldehydes are related to carboxylic acids. Esters are related to primary alcohols because you can reduce them down there. Those need to be you need to be comfortable with that. Primary alcohol, if you oxidize a primary alcohol carefully and you take out one of those hydrogens and this proton from the top and you put a pi bond here, that gives you an aldehyde. Ketones won't do this. Ketones won't do this, right? Ketones are not going to be useful in this type of sequence because they don't have a hydrogen attached. It's all about how many hydrogens attached because they're the ones that have to come off. So in this case, I formed an aldehyde. And then if you're not careful, you can go further. You can get rid of this extra hydrogen, replace it with an OH, and that gives you a carboxylic acid. There is a distinct relationship between primary alcohols, aldehydes, and carboxylic acids. And you can go from here to here, and we'll learn how to do that on Friday, and from here to here, and you can go all the way if you need to. Depends upon the reagent that you choose to use. But things are starting to get very complicated, and for those of you who are interested in, graduating, this needs to be understood. So what we're going to develop here is a whole bunch of methods to oxidize, to complement the reductions that we did last time. Starter material here, secondary alcohol. Big difference now. Secondary alcohol only has one hydrogen right there. It's all about the hydrogens on that carbon, the alpha carbon, the one that's being attacked, the one that's being involved in the chemistry. If I only have one hydrogen there, I can only take one off. So I have a difference now. If I go to a ketone, which I can, I'm not going to go any further because there are no H's. Maybe write that down. No H right there. You can't have an H. If there's no H there, you can't take it off. So primary alcohols go to aldehydes, go to carboxylic acids. Secondary alcohols go to ketones, and that's it. What about tertiary alcohols? Why no reaction? No hydrogen, no oxidation. Okay? No H. That's exactly right. So, we need some compounds. I'm going to start this off, and then we'll come back to this on Friday, I believe it is. One of the best, most powerful oxidants that we have to use, also happens to be kind of nasty, is sodium dichromate. This mixture here is lovely in terms of it's a bright orange color. The dichromate itself is a bright orange crystal, really nice stuff, but it's poisonous. So you have to be very careful here. Chromium-6. Okay, chromium-6 has caused all sorts of environmental problems in terms of cleanup. We'd rather have methods that didn't use this, but it's still very powerful. And what I want to point out before I break here is the nature of the central chromiums. We'll say that sodium dichromate is drawn like so, like you would draw in freshman chem, and sulfuric acid simply protonates it. And you get this breaking down into two molecules of what we call chromic acid. And chromic acid has a +6 oxidation state for chromium, which is quite high, right? It's a quite high oxidation state. So it's missing electron density, it would like some back. And the whole motivation for this process to work is for that chromium to go to chromium-4, to go from 6 to 4. And that energy, that sort of thermodynamic driving force, results in the carbonyl. It results in the oxidation process. So as this gets reduced, the carbon gets oxidized. We will have to think about this becoming what we call a chromate ester. We'll deal with that on Friday. And then we'll do this. And what mechanism does that remind you of? Thinking about this, that you've done an awful lot here. We have covered most of the big mechanisms we have to worry about. And so what is that mechanism? This? I asked you a question. All right, be like that. Go on, you're paying for it. Friday. Answer my question, and then I'll go home happy. Give me a mechanism that reminds you of. Elimination, but which type? It looks like an E2. You have lots of work to do. Go do it.